Alright, let's talk about angular momentum. So angular momentum is your moment of inertia multiplied by your angular velocity. What I've got on the floor here is a frictionless turntable. So it's supposed to be frictionless. It has a little bit of friction, but it's pretty good. What I need is I need a force applied outside the axis to create angular motion. So right now my axis is straight down the middle, okay? If my legs and hips move to the left, my upper body is going to go to the right. Every action has an equal and opposite reaction. So I need an external force. In this circumstance, it's called an external torque. A force is through the axis and it creates a linear change. So you push me in the chest, I fall backwards. If I push directly down into the turntable, I go up. So we need a force applied away from the axis. If you came and pushed me on the shoulder, I would spin. If you came and pushed me on the arm, I would also spin. So how can I do it myself? Well, alright, clearly I need to apply a torque, which is a force outside the axis. I can put my foot here. Have a think in your head. Do you think I'm better off pushing here, which is close to the axis, or further away? Let's try. I'm going to push as hard as I can in both situations. First, I'll start close and see how much I spin. 1.5-ish before I fall off. I'm going to produce the same force, but further away. Let's have a look. 1, 2, well, a lot faster. Okay, so I was a lot faster. I didn't produce any more force. All I did was apply it further away from the axis. Think about a door, okay? Like if this is the door hinge, am I going to push right next to the hinge? We're going to push a lot further away, okay? You can open a door by pushing it next to the hinge, but you have to produce a lot more force for the same result. So we want to have a wide stance, all right? We want to keep the force a long way away. If this is truly frictionless, have a think. Should my angular momentum be maintained forever whilst I'm on the turntable? The answer is it should be, okay? Because the body is going to remain in a constant state of motion unless acted upon by an external torque in this circumstance. If there is no friction, then what's going to slow me down? Gravity is not going to affect me doing that. It's just going to affect me going up and down. You could argue a little bit of air or wind resistance. Yes, that is correct. You are correct there. However, we're talking minuscule amounts here. Very, very minuscule amounts. So, if this is truly frictionless, which is pretty good, it's not complete, but it's pretty good, my angular momentum should be maintained. So let me ask you this question. Is my angular momentum, if I can get my balance, is my angular momentum the same here compared to when I put my arms in? The answer is yes, it is. Okay, so my angular momentum is conserved because it's going to be conserved until acted upon by an external torque or an external force. What have I changed? I've actually changed my moment of inertia, am I? Moment of inertia literally means distance of mass. Moment means distance from the axis, and inertia is to do with your body's, or to do with anybody's mass. So let's have a think. My distance of mass from the axis. Here is the axis. My distance of mass is high, a long way away from the axis. When my moment of inertia is high, what happens to my angular velocity? I slow down. So when I spin like this, my high moment of inertia, low angular velocity. Then what I do, if I reduce my moment of inertia, so moment of inertia is now low, it's going to increase my angular velocity. Like so. So what I'm trying to say here, guys, is angular momentum, it doesn't change until acted upon by an external torque. If moment of inertia is up, our angular velocity will slow down. When moment of inertia is low, close to our body, angular velocity is going to go up. What does that mean practically? Think about a diver. When they leave the platform, their angular momentum is maintained until they hit the water. What do they, because there's no friction, all right? No friction, tiny bit of air resistance. Gravity doesn't affect us doing that. It just affects us going up and down. So what do they do when they want to spin fast? They tuck in. They reduce their moment of inertia, increase their angular velocity. When they want to slow down, what do? They come out of their tuck, they get a high moment of inertia, so a low angular velocity. Another example, ice skating. Can they spin really fast like this? No, they can't. What do? Reduce their moment of inertia, so get everything really close to the axis, which increases their angular velocity. They then jump up in the air and they want to stop. How do they land? Spread. This is the axis, high moment of inertia, low angular velocity, and then the friction between the skate and the ice will eventually get my angular momentum to zero. There is basically a 99% chance that there is going to be a question on the exam about conservation of angular momentum. When we leave the platform, when we are spinning, angular momentum is going to be maintained, but when we increase moment of inertia, we'll decrease angular velocity, so we slow down. And then when we decrease moment of inertia, we're going to increase angular velocity, but the angular momentum is the same in both situations.